In this problem, the loop transfer function of a negative feedback system is given where GSHS is equal to k times s plus 11 whole divided by s into s plus 2 into s plus 8. It is asked to find the value of k for which the system is marginally stable. The concept for solving this problem is taught in NPTEL Control Engineering course in week 4 lecture 2 by Dr. Ramkrishna Pasumarthy of IIT Madras. The key concept to solve this problem are as follows. If the non-repeated roots are present on the imaginary axis, then the system is marginally stable. Let us understand this through an example. Let us have two poles at J2 and minus J2 and no poles on the right half S plane. Then the system is marginally stable. If we have poles at J2 and again one pole at J2 and poles at minus J2 and minus J2, here we are having repeated roots. Here the system is not marginally stable, it is unstable. The second point is that the Routh-Hurwitz criteria provides a method to check the stability of the system. In Routh-Hurwitz array, if all the elements in any row are 0, then we form the auxiliary equation with entries of the row immediately above. In the Routh array, if all the entries in the first column are positive and if auxiliary equation is present, then the system is marginally stable. First, we'll try to find the characteristic equation. The characteristic equation of the closed loop system is given as 1 plus GS HS equal to 0, which is 1 plus k times s plus 11 whole divided by s into s plus 2 into s plus 8 equal to 0. Simplifying further, we will get s into s plus 2 into s plus 8 plus k times s plus 11 equal to 0. Further, we get s cube plus 10s square plus 16s plus ks plus 11k equal to 0. Rearranging, we get s cube plus 10s square plus 16 plus kx plus 11k equal to 0. Now, since we have the, now we will go and try to find the corresponding Routh array. We got s cube plus 10s square plus 16 plus ks plus 11k equal to 0. Since we have the highest degree as 3, so we will write s cube in the Routh array, then we will have s square, s1 and s0. The coefficient corresponding to s cube is 1 and coefficient corresponding to s is 16 plus k. The coefficient corresponding to s square is 10 and the coefficient corresponding to s power 0 is 11k. To get the entry for s1, we will do 10 into 16 plus k minus 1 into 11k is minus 11k whole divided by 10. Then the second entry will be, here we have 0 and 0, so 10 into 0 minus 1 into 0 by 10 is 0. Similarly, we will get 0 here. The entry for S0 will be this whole term into 11k minus 10 into 0 by whole this thing, so we will get directly 11k. So as discussed earlier, we need to get an auxiliary equation. So for this we need the entries of S1 to be 0. For that we will have 10 into 16 plus k minus 11k whole divided by 10 equal to 0, which is 160 plus 10k minus 11k is equal to 0, which is k equal to 160. Once we get k equal to 160, the next part is to verify that the entries in the first column of the root array are positive. We have characteristic equation as sq plus 10s square plus 16s plus ks plus 11k equal to 0, which is now s cube plus 10s square plus 176s plus 11 into 160 to 0. So now again we will check the root array. The root array is given as s cube, s square, s1, so s0. For s cube we have 1 and we have 176. Here we have 10 and 11 into 160. So the next thing will be 0 0, okay, but we will use here the concept of auxiliary equation, which is as equal to 10s square plus 11 into 160, and differentiating it once with respect to s, we get 20s plus 0. So we get s1 star as 20 and 0, and this will be 11 into 160. We see here that the entries in the first column are positive, positive, positive and positive. Hence we can say that k equal to 160 make the system marginally stable. To solve this problem, first we have found out the characteristic equation of the system, and then we have used the concept of Routh-Hurwitz criteria to obtain the value of k.